K equal to 5 kilonewtons per meter, or 5,000 newtons per meter. And we need another assumption here. The springs are going to remain vertical. And that kind of has to do with another assumption we'll make is going to be a small angle theory, or small angle assumption. And we'll see this a lot in EMCH 213 because all the deformations we study we assume are small. So we're going to be using small angle approximation for the analysis we do. So it's originally horizontal. We're applying this 800 Newton load at C. So the springs are going to deform. So what we want to see is what's the angle that the beam makes with the horizontal after we apply the 800 Newton force. So the picture as it's here now, this is kind of right before we apply the 800 Newton load. Then the springs are going to deform. So it's horizontal before we apply the 800 Newton load. So our free body diagram for this is going to be really straightforward. So we have the 800 Newton load. We have 1 meter. We have 2 meters. For the sake of the rest of the problem, this will be a rare circumstance where I will assume that the springs are in compression. I'll just make the analysis a little bit more straightforward in the rest of it. However, you assume tension, and that's perfect. But I know since I'm pushing down that the springs must be compressed, this will make it just a bit easier. So I'm going to have the force in spring B and the force in spring A. Again, assuming compression in this case. It's in equilibrium, so these are going to be true. So forces x are equal to 0. And looking at the free body diagram, nothing's in the x direction. So 0 equals 0 is true. It just doesn't add much to our analysis. But it is a condition for equilibrium. In the y direction, I have FA plus FB minus the 800. And in this case, there's no pin, so A or B would be equally fine to take the moment about. They'll both eliminate one of our unknowns. I'd say you would not want to take it around the 800 because then FA and FB will be in the equation. But if we take it around FB, we're going to get a negative 800 times 1 plus a 3 times FB. So we can start to get some of our unknowns here from the equilibrium equations. So from equation 3, the force in B is 267 newtons. It's in compression. And putting 3 into 2. The force in A, if I can find it, 533. Also in compression. They both turn out to be positive, but my assumption was compression this time. So positive means compression, unlike usually positive will mean tension. All right, so we used up our equilibrium equations. We found the forces in the springs. So this is kind of the stuff we do automatically pretty much for any equilibrium problem. So we can at least get this far without thinking really too much. This is now the part where we have to start to think. We haven't found what we need to find, that theta value, the angle that makes the horizontal after it's compressed. So where do we go from here? We know the forces in the springs at least. Yeah.
We plug in the forces for the springs into the constant to see how much they get compressed.
Right, so we haven't used Hooke's law yet. These are springs, so Hooke's law applies. We have 2 springs, so each one will get its own equation. So we don't know the original length of the spring. We don't know the equilibrium length of the spring. So that formula, that version of Hooke's law doesn't help us. But we can use the other version where it's just K times the deformation, so how much it compresses. Again, this is under the assumption of compression. So in this rare case, delta A is positive for compression, negative for tension. So we know FA, we know K. So we're going to get 533 is 5,000 delta A. So the amount that A compresses is going to be 0.107 meters. And then we have that second spring. So delta B is going to compress 0.0533 meters. All right, so we know how much each spring compresses. So where can we go from here? This part's a little bit tougher to put into words, I think, but how can we use this information? Right, so we're going to need the difference between the two. So we see that A deforms more than B. So the left-hand side, that A side, is going to be lower than the right-hand side, and that's where we're going to get the angle from. So kind of the schematic we can draw is now what does the beam originally look like, and now what does it'll be a very exaggerated picture. But originally our beam is horizontal. We're making the assumption that our springs remain vertical. There'll be a little bit of hand waving in this next part. So we're going to push down on this, and then it's going to deflect this way. I'll make that solid. So side B is going to deflect by only delta B. Side A deflects by a total of delta A. This is also delta B. So this is where that difference comes into play, the delta A minus delta B. Now this is what we ultimately wanted, that value of theta, of how much it's deflected from the horizontal in this case. So we have values for theta B, we have values for theta A. This is where it's going to be a little bit, this is where the small angle approximation is going to be important. This beam can't change its length, so we're going to say it's 3 meters. So this is where it gets a little bit weird because the beam was also 3 meters when it was horizontal, and the springs haven't gotten any closer together or further apart when we've done this. So this can't happen where this is a right angle and it's isosceles. So geometrically, this does not make sense to be calling this horizontal 3 meters and diagonally 3 meters and have that right angle here. But with the small angle approximation, even though it's not technically possible, the error that we're going to get is relatively small, and we can double check that when we go and actually find the angle to see is that a reasonably small angle. So we're actually going to use this is more important that the hypotenuse remains 3 meters long for this analysis. So we're going to kind of ignore this fact for the moment and just concentrate on this fact that this is 3 meters from A to B, no matter how much deflection there is. So we know the tangent of this angle is delta A minus delta B over 3. So right, if we had over 100 there, then it doesn't matter. Right. So yeah, if you wanted to do this in millimeters, that would be fine, but you have to be careful that both numerator and denominator are both in millimeters or in centimeters or whatever you want to work in. Yeah, so whether it's 100 or both of 1,000, that's perfectly fine. So we know delta A, we know delta B, so we can solve this last equation here and get that angle of deflection. So we get about 1.03 degrees as the angle of deflection from the horizontal.